So as Cecilia said in the introduction, today I will be talking about practical insights for the biochar industry, and that derived from my work on life cycle assessment. So as was said, I have prepared a PhD thesis over the past 4 years, and this is available online as a PDF that you can download. And 2 weeks ago, I also presented my work in a more academic format, and that recording is available as well now on YouTube. So today, I'll not be repeating what I've said 2 weeks ago, but I will just focus on a more selection of results in a less academic style, and also be talking about a specific chapter in my thesis, which is chapter 6.4, where we give practical recommendations for the biochar industry and for different type of actors. So there will be first 3 result summaries about description of biochar systems, how to measure and describe effects of biochar, and then a few words about the climate impact of biochar overall. And from these 3 points, then I will derive into different recommendations for different actors, energy utilities, farmers and their advisors, product manufacturers that want to include biochar, and in the end, municipalities and other agencies. So the first piece of result is actually derived from our experience of performing environmental assessment of biochar, and it takes the form of a flowchart to get an overall picture. And it starts with biomass production. So the use of land to produce biomass, either in forestry or in agricultural context, but also in urban areas. And what is remarkable with pyrolysis is that many different kinds of feedstocks can be used, and they usually have different properties. Some of them can be classified as waste, some are dedicated or primary production. They also have different supply chains, and therefore they can have very different environmental performances and their environmental impacts. And finally, it's also worth mentioning that biomass feedstocks, when we consider given projects, are available in different amounts with seasonal variations and sometimes long-term variations as well, multi-annual changes. And last but not least, also physical and chemical properties of these different biomasses play a role when we study biochar systems. Then once we have the biomass, the second step is to do pyrolysis, and that may also include some pre-treatment like drying and or size reduction, chipping. Another interesting feature of pyrolysis is that it exists at all scales. We can have very low-tech reactors as shown on the left, or small ones, and then it can go to much larger scales as well. For us, when we study biochar systems here, what is important is that pyrolysis reactors can have different capital and labor requirements. They can also have different use phase emissions of air pollutants, and the pyrolysis gases and oils can be valorized in different ways. And that's what we have here. So in the most common case, pyrolysis gas and oil can be burned to produce heat, but that's not the only option. And usually the larger the reactor you have, the more things you can potentially do with your gases and tars. And then the second stream we also have, of course, from the pyrolysis is the biochar. And the biochar is used in combination with other materials to manufacture a product. And then this product has, of course, a use phase and an end of life. And there are, again, a very broad diversity of application in urban areas, but also in the rural context, actually where it first emerged in rural areas. Yeah. So we have soil application, concrete, water filters, remediation, animal feeding, and manure management are typical examples. So this being said, that's how we get an overview of biochar systems. And the first thing we realize here is that biochar production and use is multifunctional. There is a function delivered here as a product. The biochar has a function. It's, for instance, an urban greening, it's tree planting. And there's a second function delivered by the use of the tars and gases. So usually it's energy service. And then there is sometimes a waste treatment function provided by the pyrolysis. And also biomass production can be associated, at least in LCA, with what we call a reference land or biomass use. So around our biochar system, we usually depict a reference system here. And that's, if we want to have a complete description, taking into account that reference is important. Now, I want to also say a few words on how to use this flowchart, which we make available online. And one of the things here is that when we design a biochar project, we can have different starting points. If I have biomass available, I will consider first this process, analyze it, understand it, and from there build the rest of the picture. And that was, for instance, the case of the Stockholm Biochar project, but also Stockholm's Hem here in Stockholm that decided to look at the biomass that they had available and decide what they could do with it. That's one starting point. Another starting point is maybe if you have an energy need or an energy demand. That was, for instance, the case of Lindeborg's farm in our second case, where they wanted to find the best way to heat their facilities, and they considered, could pyrolysis be an option? And from there, they built a biochar project. Then we can have also a third storyline that starts with the fact that you would like to use biochar in your products. And then you're considering what properties are beneficial for your product and which biochar could deliver it, and then how to produce it. Third story, and that was, for instance, the case of many companies that have been working with us in the past years, like Vectec, Hasselfors Garden, or even NSR. Finally, another perspective, the fourth one, is that could be the one from municipalities that want to buy products that contain biochar to be able to use it in their given public procurements and in their built environment. And then they are considering what biochar should I buy, what product is most beneficial. And that's a different perspective as well. And finally, the fifth perspective is that when you try to have an overall vision of a biochar system and that, or biochar project, that's maybe when you are looking to support the sound development of a biochar industry. And that is, for instance, relevant also for municipalities, but also investors and public agencies. So that flowchart can be used and applied to specific cases. And here I'm just showing a quick example of the Stockholm Biochar project, where you can see that the biomass came from garden waste. It was pyrolyzed in a Pyreg 500 unit, and the heat was used for district heating, and the product was mainly used for urban greening. So every box can be made specific to a given application and context. And here, when it comes to the reference system in gray, what was happening before with this garden waste was that it was combusted for heat and power production in the city, and that's at this reference box here. And trees before being planted with biochar were planted using a conventional substrate made of different materials, and that's the reference we have here. And for the heat generation, the reference we have in Stockholm is that a lot of the heat is supplied by combustion of wood chips. That can be also a reference we describe here. So having said this and explained how to use a flowchart, I'm going to move to the second point, which is the fact that biochar effects are always relative. And that's related to this reference system I was just describing. To clarify, I'll take some examples from what we hear in the literature, but also in the public discourse. Biochar is known for having many different effects. And for instance, in urban areas, one effect is for biochar is to say that it can reduce our reliance on peat product, which is common in horticulture and urban areas. But this depends on a reference situation where we assume that we are using peat. Like we would use more if we don't have biochar, and if we do biochar, we have a reduced use of peat. But that's a relative effect. And in our work, we have been classifying that type of effect as a change in technosphere input, in materials being consumed in the economy. A second type of effect is related to nitrous oxide emissions, for instance. If you're in agriculture and you use biochar in your soil, it's common that you will have a reduction in emission of this greenhouse gas. But that again assumes that you have a reference situations where you're not using biochar or using something different than biochar and you get higher emissions. Here we've classified that as a change in biosphere emissions. So an environmental process that is affected. And finally, a third type of effect could be exemplified by having improved tree health and reduced mortality, meaning that there, for a given amount of resources, we have a higher output of a product, of a useful service being delivered. So here is a third type relating to the output. And I also want to add that even carbon sequestration, carbon removal in biochar is a relative effect because it depends on the reference biomass use we have. So overall, what I'm saying is that we can do a parallel with when we do a control experiment. When we do controlled experiments, we have a control. Sometimes we can define several runs to be able to measure an effect. In LCA, this notion of control is what we call a reference situation, and it's important to make them explicit. And well, when I was working and meeting with various actors in Sweden, doing my different case studies, that notion of a reference was always a bit difficult to explain. And we were, for instance, discussing it when we used peat products or compost. Why do we have to assume a reference? And why does it sometimes have such a huge impact on the calculation, on the climate impact? Well, and I came to realize that the best way to explain it is to actually refer to an example from fossil fuels. So when humans are burning fossil fuels, which we have here, we are basically emitting CO2. And in the reference situation there, if we force ourselves to define a reference, there we wouldn't have anything happening. If we don't use fossil fuels, they should stay in the ground in their geological storage and no emissions would happen. So there you see that the emissions here of CO2 are relative to what happens in the reference. And here it's a very easy case, there is nothing happening. But when we look at biomass, that's a bit different. When I'm using a piece of land or a biomass for a given application, I have not only carbon being emitted, but also other greenhouse gases and changes in, for instance, in surface albedo. It's emissions, but also uptakes. So already a more complex picture here, but the reference is also more complex. If I'm not using that biomass for my application, something will happen to it, which also involve emissions of various greenhouse gases and uptakes. And that's where, so for fossil fuels, the reference is easy, it's no emission, it's unique, there's not much else that could happen. And that's why it's very not debated at all. It's kind of agreed by everyone. But when we look at biomass, whether it is a case of compost, biochar, the use of peat, or any other bio-based product, we have a more complex process to model and also several possible alternatives. And that's why it's debated. It's debated, but still it's needed to account for it in some way. And we can use several scenarios to reflect different perspectives, for instance. So that I wanted to clarify again, that references are needed, and it's a very common thing we do in LCA. Now, the third part is regarding the climate impact of biochar, or more specifically, the climate efficiency of using biomass for biochar. This figure that I show here is taken from my thesis. I've explained it in detail a couple of weeks ago, but here the main message of that figure is that, yes, we've shown that biochar can efficiently contribute to climate change mitigation if some conditions are met regarding energy systems, regarding the stability of the biochar that is supposed to be high, and if biochar is used for a good purpose. And here I would like to clarify one item, which is that these three conditions are sometimes wrongly understood. When I say these three elements, these three hypotheses, some people sometimes interpret it as biochar is complicated and works only in few cases, but that's not what I'm saying. Instead, what I'm saying here is that these conditions imply that we must have a coherent climate strategy. We must produce good biochar the right way and use it with a good purpose, but at the same time, we need to do all the rest that is needed for biochar, for climate change mitigation, which is behavior change, energy efficiency, and deployment of other low carbon technologies. And we have to do that in the right proportions. So it's not a negative conclusion here, it's more a call for coherence that we need to have. And how does this now translate into the climate strategies of different actors? I'm going to have a couple of slides left for each type of actors I'm considering. And I will start with energy utilities, such as district heating companies in cities in Sweden or in other countries as well. In the thesis, I write that investing in biochar production capacity is a suitable investment if we assume that if we can justify that these four conditions are met. They're very similar to what I just presented earlier, but we can also be a bit more specific. When I talk about decarbonized energy systems, I talk about anything that is well below the climate impact of natural gas. When I talk about biomass being available in insufficient amount, that really depends on sometimes the local context and also future scenarios we may have. Biochar stability is very dependent on the pyrolysis process we choose, and therefore it's important to take that into account. What process am I going to design? And then after we have these benefits from biochar use that needs to be thought and optimized. The point I want to make here for energy utilities is that life cycle assessment, the work I've been doing, cannot answer all these questions. Instead, we need also additional work. For instance, for the first point, future energy scenarios, considering what happened on the supply side and on the demand side is important. For biomass availability, considering the local context, optimal biomass allocation is something to be done. And yeah, the chemical engineers who design pyrolysis process need to be involved, and also economists who do market studies are very relevant here to look at biochar use. And what I can say here is that among the actors we've met along the years, many of you have been doing these kind of studies alongside our life cycle assessment work, and that is, I find, really good. Moving on now to farmers and farmers who would like to produce biochar and heat. One first remark is that pyrolysis heating should be first considered on farms that still rely today on fossil fuel. That would be a good upgrade, a good replacement, but it also applies to farms that have old or inefficient technologies for heating themselves. And the same applies now, or to, again, about biomass, that we have to be able to secure a local and long-term biomass source nearby the farm, and have in mind that a pyrolysis plant would consume approximately twice as much biomass to deliver the same heat. And then a third aspect is what directly comes from our work in the second case study, is that dimensioning of a pyrolysis plant is a key factor, especially in small scale heat systems like we have on farms. And if it's done the right way, or if it's not done in the right way, it can affect the time, the economy, and also the environmental performance of your plant. So I have this little illustration here where we have, this is the heat demand of a farm. You see that it's, for instance, low in the summer months, and then it's high in the winter, and it's low again. And then you need to know that the pyrolysis plant always has a minimum capacity to operate and then a maximum capacity, and it can be turned on only between these two levels. So here you would see that you can operate a plant between November and April approximately. But you need to remember that the heat demand is not that smooth. There will be a lot of variations during the days, and especially with climate change, this is probably going to increase this variations. But also you must consider that over the lifetime of a pyrolysis, which is several decades, up to 25 years, the heat demand is also maybe going to change, can be reduced due to climate change, or it can be increased because you're going to build new facilities around and connect them to the heating supplied by the pyrolysis. And you should have or try to have in mind all of these different aspects when you dimension the pyrolysis plant to get the optimal size for your specific project. That can solve many, avoid many issues. Now, continuing with farmers, and now shifting to farmers who want to use biochar in their agricultural activities. One figure here derived from our methodological work, is basically saying that interactions between soil and biochar and the final effects that we get in terms of productivity or in environmental impacts are rather complex to describe and very variable. So practical recommendations here is that all biochars are not made equal. They have different properties and therefore will have different effects in your field. That needs to be taken into account. And so certification can be helpful there. And you need to know what you get when you buy biochar to use it. You should be well informed about what it is and what it could perform in your field. Another remark regarding carbon credits, because it's quite common that people would like to use biochar and also be compensated financially for applying biochar to their soil. That's a good development, it's happening. But my point here, my remark is that it should not be the sole driver of biochar use. Ideally, you should also use biochar because it provides another benefit for your soil. And then if you want to be more specific, we recommend having a problem-solving approach. What is a problem? What are the problems that you're trying to solve in your given production system? How can you alleviate a specific problem with a specific biochar? And to help you more with that, I think I will refer to two new reports. One which is a scientific article that has a very explicit title, which is how biochar works and when it doesn't, with very practical and convenient description of mechanisms. So I recommend that reading. And there is also now a report that has been released in Swedish by Hushållningssällskapet that described and maps all the effects that biochar can have in agriculture. Okay, now moving on to manufacturers of biochar products. And here, while I was in contact with different companies, I always had this question on what is the climate impact of producing biochar? Can we have an emission factor for biochar? And yes, I think the answer is yes, we can calculate emission factors for biochar, but we need to remember that it can be produced from very different biomasses, in different reactors, and in different energy contexts. And that can lead to very varying climate footprints. Here I show some calculations we had in our Uppsala case, both expressed per ton and per cubic meter. And the message here is that the range of emission factor can be quite wide, from 70 to 400 kilograms per cubic meter of biochar. And also the carbon sink, the amount of carbon embodied in that material can vary on a broad range as well. So again, the message here is that yes, we can calculate emission factors, but we have to do it in a very supply chain specific way, specific to the biochar you are using. That's a prerequisite to be able to include it in climate footprint calculation of your product, of your final product. And that leads me to the next point, which is also that when you design a product that contains biochar, the design phase is really important. And I'm going to take here an illustration. It's not real numbers that I'm going to show, but it's the process I want to explain. So let's consider here that we are manufacturing a tree pit, like on this picture, that can be used for planting trees in urban areas. And we can either do it using normal concrete, standard, which will have given amount of emissions. But then we can also add biochar to it and make what they call a charcrete mix. And that will have different properties, but also a different climate footprint. But there is not a single recipe for that. You can have many different recipes. And actually, when we worked with a Biochar producer and we tried different recipes, maybe some of them had an increased climate impact, increased emissions. But then the company worked further and developed new products and had then further recipes. And here what I want to show is that it's not simply because biochar is in your product that the climate footprint of the entire product is better than the reference. No, that is not automatic. And here, I think comparative life cycle assessment early on in the development of your product can be useful to make sure that you are in this third case here on the right and not in the first case there. So where you have here, you're getting both emission reductions compared to the reference and you are creating a carbon sink. And that's really important. I think that's what we should aim for when we develop biochar products, to be in that third case here. Having said this, another question I often get is how to communicate about the fact that we have biochar in our products. And I think here that the guideline is to be transparent. What biomass feedstock has been used, what pyrolysis process, what material properties do we have with your biochar, and what is the geographical origin of your biochar? Does it have any certificate? That needs to be communicated. And when it comes to assessing the climate footprint of a product, something I really usually stress is that you should display the carbon storage value you have calculated separately from your climate footprint. And also in your advertisement, maybe say why you're using biochar in your product beside the carbon sequestration aspect of it. So I'll try to clarify that by taking an example. Let's assume I'm producing green roofs. And then I would probably describe that my biochar-based green roof has a cradle-to-grave climate impact of 55 grams of CO2 per square meter, which is, by the way, 25% lower than my previous generation of green roof that was using more peat in it. So we are reducing it because we reduce peat use. But then I also can say that, yeah, and as a side effect, we also have in that product carbon that is being sequestered. And the biochar that I used has these properties in this origin. And then you can finish on saying that the biochar in the product has effect, for instance, on the water holding capacity of the roof, also reduces the need for fertilizer over the lifetime of the product. That's just an example, a fictional example, but to explain what I meant by these guidelines up there. Okay, now moving on to the last actors that I'm considering here, municipalities and other agencies. How to have a coherent climate strategy at the city level? Well, it will be maybe mirroring what I've said a bit earlier, but now it's a different perspective. Today, a city has greenhouse gas emissions, and tomorrow in the future, we want to reduce them drastically, for instance, to meet the Paris Agreement goals. And at the same time, you may want to create carbon sinks to reach fully net zero emissions or longer climate targets. So here you see that we have two goals, reducing emissions and creating carbon sinks. And the biochar products you deploy in your city should ideally be able to do both of these goals, reducing emissions and creating carbon sinks. There is no point in creating a carbon sink that will increase significantly your emissions. And here the message is that probably that biochar is one of the few techniques, the few removal techniques that can achieve this double goal if it's done properly. And again, life cycle assessment is what can help you determine whether the specific biochar strategy you deploy is going to help you achieve the double goal we have explained here. Okay, so that was it for me. I have one last slide that I'm going to repeat here, saying that biochar has different starting points. It can be from the biomass, from the energy side, it can be from the product side, from the use side, or from the overall system perspective. And maybe that was my role in the past 4 years, to have a look at the entire picture and interact with so many stakeholders. Yes, so thank you for that. And now I'm going to stop the recording.